Was geht ab, Berlin? Seid ihr gut drauf oder was? Okay. Okay, so today we're going back to kindergarten. We're learning to draw. We're not using crayons though. We're drawing onto the camera with JavaScript. So a bit about me. I'm Marc. I'm running an agency called Margelo. I'm not sure if you've seen some of my repos before. I'm maintaining VisionCamera, React Native Blur Hash, React Native MMKV, and a bunch of other libraries. I also contributed to React Native a bit. Yeah, so, okay. Why do we want to draw something onto the camera? Like, what's this about? Well, there's multiple use cases to this. For example, you might want to render some real-time overlays, you know, some bounding boxes, some object detection. You want to detect a banana or a Red Bull, maybe in this case. In a real-world use case, you probably want to detect a QR code or you know, some other like shapes, draw shapes onto the camera. You might want to render some real-time effects. In this case, I'm doing a blur filter where it just gradually, you know, blurs the image and removes the blur again. Maybe color filters. You know, in this case, it's just a reddish look color filter. Some real-time overlays, which is actually, you know, this is from a client app that we've worked on, where you can create animated stickers of the foreground. In this case, it's just a hand, and it removes the background. So in this case, it just dims it to still show the user what's happening. Or we just draw some, you know, Snapchat-style face masks or filters. In this case, it's a, you know, image, like a face blur example. And yeah, so, you know, this looks pretty complex. How do we usually do this? So I'm calling this traditional, you know, it's not outdated or anything, but, you know, before VisionCamera, you would build this completely natively in iOS or Android. And let's just take a look at how it would work on, you know, native iOS. So it is pretty complex. I'm not going to go into, you know, details about this, but essentially you just create an AV capture session, you create the video data output, set it up with RGB, you know, with the video resolution that you want. You create a metal device, you know, the metal context, command Q, view, everything. You create a secondary metal device, context, command Q, and a pass-through shader. Then you run some frame analysis. In this case, maybe, you know, a face detection algorithm, some ML kit, object detection, whatever you want. And then you render the frame to an off-screen to the off-screen context that we created. Apply your, you know, image filters, whatever you want, using metal, you know, with Swift or Objective-C or whatever you want. And then you render the result of the off-screen context to the screen using display link. So this is a lot. It's pretty complicated because camera and graphics APIs in native iOS are just very complex. It's very verbose, so you need a lot of code to do this, and it's hard to maintain. You know, you can't, if there's like a problem, you need to fix a bug or anything, you would need to completely, you know, dive into native code, fix the change, rebuild your app, deploy the thing to the App Store again. So it's hard. Also, what about Android? Well, on Android, you need to basically rewrite the whole thing. You need to use Java or maybe even C or C++ and OpenGL instead of Metal. So you would need to maintain two code bases. Well, okay, React Native to the rescue. The React Native ideology is you learn once, write anywhere. In this case, you write once and run it on iOS and Android because we only want to write our camera app once. And the important thing here, because we're dealing with real-time effects and, you know, some processing, we don't want any performance compromise. So we want to make this fast. We want to make it as fast as possible. And, you know, traditionally in React Native, you had some issues with, I don't know, bridge being slow and passing stuff around. So we don't want to make that compromise. So here's where VisionCamera comes into play. VisionCamera, or React Native VisionCamera, I often just, you know, call it VisionCamera, is a fast and powerful library for React Native, and all of the complex concepts or constructs are abstracted away in a nice JavaScript API. So stuff like video, photo, snapshot capture, which is pretty complex on a native side normally, you know, with setting up the video queue, streaming the buffers, making sure that the output file is correct, you know, dealing with the codecs like H.264, H.265. It's pretty complex. So all of that is abstracted away in a nice JavaScript API. Buffer compression, pixel formats, all those kinds of things you don't really need to worry about in VisionCamera. and frame processors, which I'm going to explain in a second. So just a fun little picture here. On the left side is the iOS implementation of start recording, the function calls to start a video recording, which is, I don't know, what is it, like 100 lines of code? And on the right side, you just call it in 4 lines of code in React Native. This is the code base of VisionCamera, so it's on Android and on iOS you have a bunch of files, and on the right side this is a screenshot taken from Shadowlands, an app I built, which is just a few lines or a few files of React Native TypeScript code. Okay, frame processors. So as the name already suggests, a frame processor is a function that can process a frame. In the case of VisionCamera, it's a JavaScript function. So on every frame that the camera sees, under quotes, the JavaScript function is called. They are, in React Native VisionCamera, powered by worklets. So I'm not sure, is everyone familiar with what a worklet is? Hands up if you've heard of worklets. Okay, so just a quick explanation. Worklets are just JavaScript functions that are moved or copied to a separate JavaScript context. So you have 2 JavaScript contexts running, and they can, run in parallel. So it's not really multi-threading for JavaScript, but more like multi-processing. And frame processors are synchronous and, most importantly, fast, because we don't want any of the bridge traffic. We don't want any serialization or anything happening. They need to run instantly, because otherwise the camera just blocks. It's not real time anymore. So here's an example of how a frame processor looks like. It's a simple JavaScript function. You use the hook I created, use frame processor. You have an argument called frame, and the worklet directive basically allows the function to be moved to the separate worklet context. So in this case, we're just logging the dimensions of the frame, which will be called, like in a normal camera, probably like 30 times a second, because cameras are usually 30 FPS. So in this case, 30 log statements will appear in the log console per second. And the rest is magic. I mean, you just pass the frame processor to the camera component, and VisionCamera will automatically, set up the video context, the video queue, package the frame into the proper format, and call your JavaScript function. So, here's just for the full example. You just pass the frame processor to the camera. You can configure the pixel format to be RGB or YUV, which is a more compact format, and configure the FPS as well. Okay, so the frame argument, the parameter you get in your frame processor is the actual frame that your camera sees. So it holds all of the pixels from the camera. And every time the frame processor is called, you get a new frame. So, that's a lot of data. In a single 4K frame, most cameras are 4K, they are 33 megabytes, one single frame. So at 60 FPS, there's 2 gigabytes of data just flowing through your JavaScript function. And, those frame processors are not only like running for a second, they're running for minutes. So that's like huge amounts of data. Here's the challenge. We need to send the frame to JavaScript, and it needs to be fast. So as I mentioned before, 2 gigabytes per second cannot be serialized or base64 converted. We can't really use the bridge for this. So instead we use JSI, which I'm going to explain in a second as well, to synchronously pass the frame from C++ to JavaScript, which happens by passing the C++ frame as a reference. So we're not actually packaging the 33 megabytes into some format and then copying it over to JavaScript, but we're just having a reference, a C++ reference that we're exposing to JavaScript, and then through JavaScript you can access stuff on that reference. So JSI is the synchronous layer between C++ and JS. It's what powers the new architecture. It's what powers many modules nowadays. Essentially, you can just call C++ methods from JS and JS methods from C++. So just a round trip, without any asynchronous batching or any stuff like that going on. It's just a synchronous layer. It's not as fast as FFI, but that's a different topic. And JSI host objects are just C++ objects exposed to JavaScript, so I can pass them by reference. Right. So what can we do with the frame? Well, currently I expose these properties and methods. So you can access the width, height, pixel format, whatever you want on the frame, timestamp orientation. And you can also, as you can see here, to array buffer, you can also convert the frame to an actual array buffer which is pretty fast. It's still a copy, but it's pretty fast. Right, so we theoretically have the pixel data in JavaScript. Now, how do we run the actual frame processing? Well, this is a bit difficult to explain because it is a hybrid approach. We don't want to run the actual frame processing in JavaScript because, as we all know, JavaScript is pretty slow. So we want to run the business logic in JavaScript, which is, we decide what we want to do. And the actual high-performance frame processing should be done in native. So, we still have the flexibility of configuring our plugins in JS, but not, compromising performance here by making all the plugins native. So what exactly is in native then? Well, first of all, it's VisionCamera's core code base, which is pretty obvious. That's already native code. So all of the, video queue setup code is in native code. And native code is, by the way, Swift on iOS and Java or Kotlin on Android. And C++ layer in between. And also, frame processor plugins are native code. So if you write any frame processor plugins, maybe in your app, or you use some third-party libraries, packages, they are in native code as well. The benefit of a frame processor plugin is a simple native function that you can plug into your frame processor. So inside your JavaScript frame processor, you can call 1, 2, maybe 10 different frame processor plugins, which are essentially similar to native modules, just a single native function that takes a frame and returns a result. So, whatever you do in between that is up to you. Often they're just, single Swift or Kotlin files and just wrappers for existing libraries. For example, Google ML Kit has some nice face detection, object detection algorithms, which you can simply wrap using a single Swift or Kotlin file. And then you can call them directly from VisionCamera and get, faces or objects in the single frame. Here's an example of a Swift frame processor plugin that uses ML Kit. It is a bit pseudocode, so it's not accurate. It's not a full example, but essentially you just, in Swift, you create a single Swift file, you create your whatever processing you want. In this case, ML Kit, we do face detector.detect, and then we just return the results to JavaScript. Sorry. Frame processor plugins are fast because, as I mentioned before, native languages are usually faster than JavaScript. There's many reasons why. So just as an example, C++ or other compiled languages often have loop vectorization, lower allocation overhead. There's just a bunch of things that native languages can do that JavaScript simply can't do currently. And also in native we can use a GPU. So we can, for example, use OpenGL, Metal, or whatever you want to run your actual machine learning or AI, whatever algorithm you want. Okay, so now that we know what part of our app or what part of VisionCamera might be native code, what's actually in JavaScript then? Well, for example, it's your app's business logic. It's related to the camera, obviously. The entire app is in JS, but you relate it to the camera, your app's business logic, setting up the camera, requesting permissions and stuff like that. Configuring outputs, like the resolution of the video stream. Do we want it in 720p? Do we want it in 4K? Maybe even lower resolution. The FPS, maybe 130, maybe 60, maybe even 120 FPS for slow motion. And then we configure or initialize all of our native plugins. For example, we want to configure the face detector to be either a fast or an accurate model. And then we decide what to do with the result. So for example, here's a quick code example. We use the face detector, which is a library I'm going to link later. And then we can configure it to be either fast or accurate. And accurate would be a bit slower, but detects more faces. And then we just run the detect faces function in our frame processor, which is the function that gets called like 60 times a second, maybe 120 times a second. And then we decide what to do with the results, which in this case is just log all of the faces to the console. Okay, so back to kindergarten again. How can we draw? You might want to, or some people try to set React state. So they run the frame processor, which is called, again, 120 times a second. It's a hot loop. And then they set React state all the time, which is, as you might imagine, really, really slow because you're thread hopping from the camera thread to the JS thread and also doing the entire React reconciler and diffing algorithms. So it's getting really slow. And then, in this case, maybe a bit of explanation to this. We want to render a, a red box around the user's face. So we set a state to move the view to the user's face. An alternative would be to use reanimated shared values, which is better. So it's a fair approach because reanimated is fast and it's a great library. But still, I'm not quite happy with that. So in this case, we would also just move the view over to the user's face. So there's two problems with both of those approaches. First of all, drawing was never fully synchronous, meaning we detect faces. We have a face here maybe, and then I might move already, so the camera already shows my face in a different position, but the view is still in the old position because it's just not fully synchronous. And also, drawing was limited to views, so we can only render maybe, I don't know, a red rectangle, but we can't render any shaders, any effects, any custom paths, unless we use SVG or something, which is slow again. So we need something that's more flexible and fully synchronous. So we want to draw freely and synchronously. How can we do that? Skia. So Skia is a 2D graphics library developed by Skia Incorporated and then acquired by Google. And it's focused on drawing, not rendering. What does that mean? Well, rendering would be something like showing a view, showing a box, showing this and that. But drawing is more like a free style almost, like line paths. You can draw shapes as you want. You can render shaders, and all those kinds of things that make more sense in a camera use case in this example. And React Native Skia, developed by Shopify, by William and Christian, is a React Native library that bridges Skia to React Native, also using JSI. So here's a use case example of how that might look. You create a rectangle. In this case, again, I'm using the red rectangle example. You create a rectangle, give it some coordinates, set the color to red, and then just draw it to the canvas. Okay, so here comes the exciting part, which I'm building up to since the beginning of the talk now, and that's VisionCamera and Skia. So in VisionCamera v4, there's a new feature, which was released like 2 weeks ago, maybe. And this is the first time I'm talking about this. It's called Use Skia Frame Processor. So the difference is, we saw Use Frame Processor before, but Use Frame Processor is read-only, as in you get your frame and you do whatever you want with it, but you cannot write anything back to the camera. Use Skia Frame Processor, however, can write back, on the quotes, to the camera by drawing to the frame. So you can actually draw into the frame, into the camera frame, and it's fully synchronous. There's two concepts here, or two render pipelines that I created, which is, first of all, the camera thread. So there's two threads running. The camera is running on its own video queue, which runs completely in parallel to the UI and to the JavaScript thread. And frames are, they're on the GPU. They're streamed in 33 megabytes per frame, which is 2 gigabytes a second. So they're all on the GPU. It's a GPU texture, which is converted to a Skia texture. So a texture that can be drawn using Skia, and then rendered to an off-screen Skia context. I can render as often as I want, basically. So if the camera is running at 30 FPS or 240 FPS, it doesn't matter. I'm rendering to this one Skia off-screen context. And then in parallel, on the UI thread, we are just taking the most recent result from the off-screen context and displaying it on a Skia preview view. So it's basically just doing a pass-through render, which is tied to the display's refresh rate. So 60 FPS or on modern phones, 120 FPS. But those are two separate pipelines that are running. And you're only drawing in the camera thread. The UI thread is just a copy over. Okay, so let's build a real-world example. Let's build the face blur app in just 1 minute. As a quick overview, there's 3-4 steps maybe here. First of all, or maybe 5 steps. We need to install all of the libraries, obviously. React Native VisionCamera, React Native Skia, all those kinds of things. It's all in documentation, by the way. So if you want to check that out, react-native-vision-camera.com. So step 1, we initialize the face detector plugin. We saw that before, and prepare our blur filter. We detect the faces. So inside our frame processor, we detect all of the faces using the face detector plugin. So that's the actual inference. That's the actual hot loop that's running on every frame. And then once we got our result back, so once the frame processor face detector plugin, face detector plugin gave us our results. We can iterate over each face in the single frame, get the face coordinates, and then draw the blur filter onto that face using the coordinates that we got. Okay, so step one, we initialize the face detector, which is using React Native VisionCamera face detector, a library built by Louis, I don't know what his name is, but this GitHub user, he's amazing. And we configure it to be the fast algorithm, not the accurate algorithm. Most of the ML kit libraries have fast or accurate. Accurate is more for still images, it takes longer to process. Fast is for real time. And then we configure it to give us contours, which are the individual points in the face, no landmarks and no classification. Cool. So we set that up, it's a hook in our camera page. Then we prepare the blur filter. In this case, it's a Skia image filter. We can configure the blur radius. So in this case, it's 25. And then it's just a paint that we can apply to our rendering pipeline, I guess. Right, so step 3 would be to actually run the Skia frame processor. And inside this Skia frame processor, we just detect all of the faces. So this is, again, the hot loop that's running on every camera frame. And then once we, as a result, we get faces back, which is an array. And then we iterate through each face and just create a Skia path that, follows the line of the face and then draws the blur filter only within that area. So the final result, it's on GitHub, by the way, is just 40 lines of code. It's very flexible, so the blur radius variable we just created can be changed on the fly. I can change it from 25 to 30 to make the blur more intensive. Hit Command S, it saves immediately, no rebuild needed. You can deploy that over the air without any native rebuilds. I can configure the plugin to be fast or accurate, however I want, and just ship it immediately without any native rebuilds here. It's insanely fast, so this entire blur algorithm runs with the face detection algorithm, runs in 10 milliseconds, which is 100 FPS, yeah, so, it's just 10 milliseconds. It easily runs at 60 FPS, so in this case 100 FPS, so it's fine for deploying it. Most camera apps, actually Snapchat only uses 30 FPS or even 25 FPS, so, the bar is pretty low. And it also runs on Android, so that's the cool thing. Skia is cross-platform, VisionCamera is cross-platform. It's implemented on both platforms. So the same thing without any changes. You just hit run on Android and it's there. You can tweak the blur filter. It's applied on iOS and Android. Cool. So other VisionCamera use cases, just as a side fact, it's not only limited to face detection or object detection or real-time frame processing. It's still a camera library. It has custom device selection. You can select between the 3 back cameras on your phone or however cameras you have. The ultra-wide, fisheye, blah, blah, blah. There's advanced photo capture, things like HDR modes, quality and speed prioritization balances, custom resolution, 4K, 5K, whatever you want, or whatever your device offers, I guess. Video capture with true 10-bit HDR instead of just double capture HDR or EDR short, FPS selection, blah, 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 all those kinds of specific features that a camera app nowadays should have. And to show all of those features, I built Shadowlands, which is just a simple app I built in my free time. You can check it out if you want. It's in the App Store and Play Store, which showcases photo capture, video capture, and FPS selection, format selection. Cool. So future of VisionCamera. I mean, VisionCamera is one of the most used React Native libraries. It has been featured in Facebook posts and everything. It has more than 5 million downloads. It has 6.5K stars on GitHub. I don't know why I left it in there, but it's a cool metric. It's used in many production apps, and many of our clients at Margelo actually use it and sponsor the development or the future development of VisionCamera. So if you want to try it today, all of this is released. VisionCamera v4 is out. It's on GitHub, React Native Skia is on GitHub, and the face blur app we just built is also on GitHub. Special shout out to William Candelon. He's not here today, but he helped a lot on the Skia side. Yeah, he basically helped, landing all of those required changes in React Native Skia, so we can bridge VisionCamera frames to Skia textures. And yeah, follow me and my agency on Twitter if you're not doing that already. And that's it. Any questions? Thank you.